In what follows are displayed illustrations of the DeConvNet method. The original pictures can be found in the ZFNet paper. On the right, each 3x3 square corresponds to a given feature map in the second layer. For the given feature map, the 9 images in the validation set that activate the most the feature maps are displayed, still on the right. Then, for each image, the DeConvNet approach is used to obtain a stylized image. These stylized images are displayed on the left. These stylized images are useful to understand what activates a feature map, what a feature map can detect. For example, at the bottom right square on the left picture, you can see right angles. This corresponds to images that indeed contain right angles. Therefore, one can conclude that this feature map is able to detect right angles. We could also try to interpret the other squares that can detect squares, parallel lines, and so on. Here are the same kind of pictures, but for feature maps in the third layer of the network. You can see that the shapes that are detected are more complex than in the previous layer. For example, on the top left, the feature map is able to detect grids or line intersections. As we go through the network, we obtain the same images but for feature maps in layer 4. The stylized images become more and more complex. The feature map on the top left seems to detect dog faces. Considering now the fifth layer, we see that the images that activate the most one given feature map are very similar in terms of content. This proves that as we add layers in the network is able to detect more complex patterns and to build a representation of the images that is well adapted to understand the meaning of an image. The first layer detects the most basic information, while the last layer are able to aggregate the information to build more complex representation of the images. We can now use the DeConvNet approach to improve AlexNet. Here you have on the top the first layer feature maps from AlexNet, and at the bottom you have the first layer feature maps of ZFNet, which is nothing but a modification of AlexNet. You can try to detect what are the flaws of the AlexNet feature maps. There are two differences between these networks. For ZFNet, a smaller stride and a smaller filter size are used compared to AlexNet. This results in more distinctive feature maps and fewer dead feature maps. Indeed, on the top, you see that many feature maps are of the same color, which means that they are not able to recognize any specific shape. Contrary, on the bottom picture, you see that almost all feature maps are able to recognize some shapes and that they are able to build more discriminative representations. There is more diversity between the feature maps on the bottom. This was done for the first layer, but we can also compute the same for the second layer of AlexNet. Here are the stylized images for the second layer for AlexNet on the left and ZFNet on the right. Again, you can pause the video and try to detect some problems in the left picture. On the right, we see that there are less dead neurons and the shapes that are recognized are more complex. Besides, there are no aliasing artifacts. If you look on the left picture at the last line and the third column, you see that this feature map is pixelized. This is known as an aliasing artifact. We do not want to obtain such feature maps because they are not able to detect very precise patterns. As you can see on the right, these aliasing artifacts has disappeared. The differences between the feature maps in AlexNet and ZFNet are due to the two modifications previously mentioned, a smaller filter size and a smaller stride. Modifying the stride helps to prevent aliasing artifacts. With these modifications, ZFNet performances improve over that of AlexNet, as we are going to see in detail. Here is recalled the structure of ZFNet for completeness. This is the same structure as AlexNet, but with a different representation.